Stars so bright in the sky. On Arizona nights they fly. Nebulae in colors rare. Galaxies beyond compare. Sky tour in the night so clear. Brings the universe near. Real-time wonders to see. Streaming live for you and me. Lift your eyes to the skies, universe in all its light. Sky tours bringing the views. Every night feels brand new. In the dark, the night unfolds. Stories of the cosmos told. Through the lens, a distant dream. Living real like a gleam. Far away, up so high. Across the stars, beyond the skull. Through the lens, a distant dream. Living real like a gleam. Lift your eye up so high. Across the stars, beyond the sky. Sky tour shows us the way. Every night a new display. Lift your eyes to the skies, universe in all its light. Sky tours bringing the views. Every night feels brand new. Lift your eyes to the skies, universe in all its light. Sky tours bringing the views. Every night feels brand new.
Okay, there we go. Hey everybody, how are you? Welcome to SkyTour live stream. It is I, Mark, and Daryl. Say hi, Daryl.
Hi, Daryl.
Hi, Daryl.
Hello, everybody. And a big howdy.
Yeah, I want to say hi to folks that have joined us. We have Tim F. was number 1. Nice job, Tim. You're the man. Okay, and followed by who was the next guy? Oh, Sam S. came in. Sam's with us. Old schools come in. Keith Evans. Hey, man. How you doing? We are shooting Measure 11 right here. That's what you're seeing up there. And just again, for the record, I'm looking left and I look right. Okay, because I have a big curved screen in front of me. So the left side is the observatory feed and the right side is the broadcast feed. So I'll pay attention to both sides of the screen. So if I look here, I'm looking at the same thing that you're seeing there. Just so you know. Hey Stuffy, what's happening? Thanks for joining us. We're looking at this guy. Yeah, we got some pretty good numbers tonight there, Daryl. At least we haven't got wind showing up. And let's go look at the AllSky.
Have you run a focus yet?
I did. Okay. The moonlight is this right here. The moonlight is just impacting this. We would see clouds up here if they were there. We have a plane going through there, as you can see. We have a satellite that came through there. It's probably going to continue to show up over there in the next frame. Actually, it did. That's pretty cool. And there's our Milky Way. Beautiful. These are the lights of Phoenix, 75 to 80 miles away. You cannot see those with your eye. Only a sensitive camera during a time exposure will show them. And we're shooting 15-second exposures, which you can see right here.
Oh, I bet they were visible.
I'm telling you, having been there 1,000 times, they're not. You can't see them. You can't see them with your eye. You can only see them with the camera.
I know Arizona's trying to be, light pollution friendly.
Yeah.
I can drive about 150 miles east of here to the Kansas line and get off the highway and down a country road, give my eyes a few minutes to dark adapt, and I can see the light domes over Denver and the Springs and Pueblo, just bigger than life.
Oh, I was in Hewlett, Wyoming, and Gillette, Wyoming, 80 miles away. The lights were just barely visible behind Devil's Tower. In fact, they silhouetted it you couldn't see it with your eye, but when you took a picture of it, there it was. Tiffany, what's going on? How are you? So let's zoom in on Measure 11 here. We've taken a bunch of them right now just to see how they're going to come out. I'm going to enhance them right away, and this will stick with us. Watch this. Ready? Boom. Instant improvement. Okay. Measure 11 is right near a star cloud, so we can see that there's lots of stars here that are also involved in this. On top of that, this cluster is often mistaken for a globular cluster, but it's just a very tight, open cluster, which differs by the fact that the open cluster has a many times smaller, several orders of magnitude smaller number of stars in them, and they formed as part of a nebula that they formed within, so the composition of the stars are all pretty much the same, but they did not form a tight ball, or they didn't form around a potential black hole, which might be in the center of these globular clusters.
Somebody saw that and said it looked like a flock of wild ducks.
Yeah.
Which is why it's called the wild duck cluster.
It had to be someone who hunts.
Or bird watcher.
Yeah. It had to be someone who hunts, maybe. Or, maybe a bird watcher. Yeah, as you can see, we got some red up here. That's because the sunset light is still with us. Old school, yeah. Hit the like button. Everybody hit the like button. If I could, I would. Alright. So, I'm looking at that guy. I'm going to just name this. I did not mention to Izabela that well, I did in our chat. I mentioned we might be doing this.
It's 6:12 a.m. in Bulgaria right now, so
Yeah.
she may not be up yet.
Yeah.
She tends to get up rather early.
Yes, she does.
Like 7 or 8, I think, her time.
Yep. I have some leftover labels that keep showing up there. That was not Measure 4, it's Measure 11. Hey, Maddie, what's up? Nice to see you. Thank you for coming on out. Tiffany, how is Mike doing? Alright, we're going to... this is only a 12-second shot of this. So, the star cloud is barely visible. But if we actually just do this, we'll save it right now. Save exactly as seen. And then what I'll do is clear this after giving us a 20-second exposure.
And leave your gain on 0?
Well, the gain has been 0. That's correct, and that's it's a test. I'm going to change that in just a second, though. Right now, I'm doing it as if it's the sensor is not beyond its base sensitivity. I'm always curious what it's going to look like. Tricia Ferreira's with us. Hey there. Look at that. The base sensitivity, and you still see dark nebula, Daryl. Look at that. With a 20-second exposure. That's not bad.
I see a little squiggle down near the lower left corner.
Yeah, right here.
Yep.
And there's some right here. Yeah.
Well, we're roughly in the plane of the Milky Way.
Yeah, we are.
Yeah.
So that's pretty. So what I'm going to do now is I am going to... I just wanted to see this. I'm not going to save this. Actually, I will, just to be complete. Okay, I'll save it. And then what I'll do is I'll clear it. But first I'm going to... pause this now, and I'm going to increase our gain to 150. So there's 150. The gain can go to 450. Okay, now we'll clear, and let's start again and see what a gain of 150 does for the same 20-second exposure. We'll be able to compare the differences. He's doing well, just busy as usual, Tiffany says of Mike. All right. Wow. Let's color correct. Let's get rid of you. Get rid of you. Hey, it's nice that my computer's protected. All right, we're color correcting now. And now let's bring this over just to our peak. Okay, see the difference? We went from 0, where you couldn't see any of this black stuff, to the straight 20 seconds. Actually, the 20 seconds showed hints of it, but at 150 we can now see the star cloud and a lot of the faint stars that just were elusive to us. That's pretty cool. Nice. And if we actually want to penetrate into the middle of this, so it looks like white blobs, I can actually make them individual stars by pulling this mid-level down, and you'll see what happens now. The stars become far more visible. You notice that the stars are also, most of them are bluer than the surrounding stars. Couple reasons for that. Primarily, one of the reasons is they're younger, therefore they're going to be bluer. Another reason is the cluster might be closer to us than the star cloud behind it, and there's interstellar reddening when you have dust between us and the distant stars. And if we look at this particular cluster, its distance is 6,200 light years from us, and the star cloud behind it is a lot further by, oh gosh, probably another 10,000 light years maybe. That's a gorgeous picture.
Cluster stars are all about the same age too.
Yeah.
And they're young blue stars.
Yeah. There are some red stars in here though. And I'm wondering if those are supergiants and if they're actually in this cluster. They may not be in the cluster. They might just be superimposed.
They could be early stars
That evolved.
heading toward the red end. Yes.
Yeah, they could be red giants.
We see it in other clusters.
Yeah.
Double cluster, for instance, have some of the first stars heading into a red giant stage, I guess.
Yeah. Hey, Marco. Hey, Judy. This is nice. We're going to go as long as we can tonight because we do have some high clouds out in the northwest of us. And up north, there's storms. And right now, the clouds in the northwest are holding the ones in the north at bay, which is kind of interesting. The moon is going to set here shortly, and that'll improve our night sky here. All right. And to those wondering and who have asked, I'm working on trying to figure out how to go live with that AllSky cam so everybody can see it at any time, because it works during the day too. Well, look at that red star. That's beautiful.
Yeah.
Let's see if that star shows up. What is that red star? Here it is. How about that? That's just a... It's just a Hipparchus star. 92391. We have its spectral type. Yeah, it's a giant. It's a K23. That's pretty cool. This is our field of view for those that don't remember. So this is our field of view. This red box corresponds to this square right here.
What's the distance on that red star?
Let's go back and see if we got a distance.
Couldn't quite read it.
Yeah, it says it's
1430?
Yeah, 1430.5. How about that? So how do they say 1430.51 plus or minus 80.3? Well, that's almost useless then. Just say 1431.
So it is far in the foreground.
Yeah.
Compared to MSA 11.
Yeah, which is 5,000 light years past it. And then the star cloud behind it's probably 10,000 minimally light years beyond that. It's incredible. So there you go. That's pretty cool. Measure 11 is pretty as always. We'll color correct one more time here. Wow, so you could actually, if you could go into space, you would actually sail around that cluster and never reach these stars here. You'd pass this one first and then zoom in and circle around. That's something that we've done. We have a 3D product that we like to race around in and show people. But I'm not running it at the same time now because it takes a lot of time and we see fewer objects that way. Okay, Measure 11 looks really pretty.
Trisha, check your settings on YouTube. She says the live stream's blurry for her.
Okay. You could be running at a lower resolution. Check your settings, like Daryl just said on YouTube. The little gear icon over on the right of the stream. And click it and see if it says 1080. It may just say auto. Just click on 1080 and you'll see, you should be able to read all this stuff on the screen here.
YouTube's really been messing with me for a while now.
Okay.
It tends to choke. Bump me down to 144 resolution. Especially in the mid-late afternoon, early evening. I don't know if that's demand on their system or
yeah.
if they're just putting a squeeze on me or what.
Yeah, I don't know. Okay, so here is 20 exposures here. We'll save exactly a scene. Alright, now we're going to pause this one more time and do one more test. Again, we're at 150. Now we're going to go to 250, and which is what we like to run at. That's the gain is now 250. And
there's Izabela. Hello, Izabela.
Good morning, Izabela. And for those who just wonder, on our screen, this here is the exposure field, and this is the gain field. This is what we're talking about. The exposure is 20 seconds, as you can see, and the gain is now set to 250. Okay, and now we're going to be taking a picture at 250 for the same amount of time, and we'll see the differences between the 0 gain, the 150 gain, and the 250. Okay.
Do you need to hit resume?
Yeah, I do, but I gotta, you know.
Oh, you gotta clear it first?
Yeah. So right now we have 20 seconds. We have 250. Now I'm going to clear, and it's going to automatically start doing it again. So now we'll see the results of the first one right here. All right. Now we do have a moon out, but that's okay. Our filters cover most of the moonlight. But let's come over here and let's... You can immediately see, down in here now, you can immediately see a filamentary structure in this dark nebula. And up here, with the very first exposure, this was not visible with the previous exposure at the lower gain. So you see the gain allows us to take in sensitive details that might be otherwise lost. And so that's what we're doing. And I'm going to move this up a tiny bit. So you can see now variation now in the texture and the color in this distant scutum star cloud here.
What is a scutum?
What is it?
Yeah.
I don't know, actually. I'm sure you'll tell me. Is it a shield?
It is a shield.
Okay.
I forgot what it is. It's usually portrayed as like a Roman infantry shield. You know, the big kind of rectangular shape, and it's got a curve across from side to side.
Yeah, and of course, Stellarium doesn't show it that way at all. But that's Stellarium for you. Stellarium's the only application I've ever used that names the stars whatever the heck it seems to like to name them. I've never seen the names of the stars with the same variation in other programs. This K23 here is a very, very beautiful star. It's a giant, about 1370, is that what we said? About 1400 light years away.
14 something, I think.
Yeah. Yeah. Not bad. So we have 7 stacked here. We did a bunch at 0 gain. We're doing a bunch. We did a bunch at 150 gain. Now we're doing some at 250 gain. And you can see the differences in capability with the different gain settings for the same amount of time. Hey Goblin, what's up? Victor Anthony, how are you? Nice to see you.
Just my imagination, or do the stars look a little less blue? Are they saturated?
They're probably going to get
higher again.
Yeah, they might be saturated. Let's see if we can change that by moving this mid-range value down and drop the brightness in the center. See? Now they're blue. So that's the nice thing. We have a lot of what's called dynamic range. And that means that we have an awful lot of leeway to go to very bright and very dim and still catch a lot of faint detail and also keep us from blowing things out because they're overexposed. All right. Well, it looks pretty, Daryl. That's what I have to say.
Oh, yeah.
All right, we'll do a dozen of these and then move on. I don't know how long we'll have tonight, but I'm thinking the forecast calls for clear skies out there, but there's storms all around us. We're in a hole, and that makes me nervous, as it should. Yeah, we might check out Saturn tonight.
Saturn is in opposition.
Yeah.
Well, last night actually, but one night won't make a difference. In fact,
Right.
I went out at 1 o'clock in the morning and timed it, and yep, Saturn crossed the meridian right at local midnight, 1 a.m. Daylight Savings Time.
Mm-hmm.
But weeks to either side, you won't be able to tell any difference. Weeks to months. Saturn will tend to go away fairly quick, though, as it's moving retrograde right now because we just passed it. If you saw a diagram with the sun at the center of two circles, concentric circles, if you do a line from the sun through the Earth, Saturn just passed through that same line last night. You could imagine it if you're on a racetrack, that Earth just passed Saturn, and it's going to start falling behind us now.
Yeah, we go faster in our orbit than Saturn does farther out.
Yep.
Okay, so we're going to clear this now. We just did that, and I saved it. And we'll come out of our deep sky mode and go back into our low light mode. All right, and then we'll be able to move to something else.
Curtis Howard is here.
Hey, Curtis. Nice to see you, man. Yeah, thanks for joining us, Curtis. All right. Let's go check out from our planetarium connection here. We're up here looking at Measure 8, otherwise known as the Wild Duck Cluster for some crazy reason. All right, I want to do something actually. I feel like trying to seahorse again.
Maybe you ought to do a mosaic. You see that image I sent you a couple of days ago?
Yeah.
I had no idea at the time what was just off screen to our left.
Yeah, well, there it is now. We'll just go give it a try. I may just... Izabela had a horrible time trying to process it, as did I. I think that maybe we need more time and a higher gain. So there it is. That void right there, you can't miss it. Izabela was writing in Bulgarian, everybody. It's okay. But you know what she was saying?
Yeah, we both posted the link to the server.
Yeah.
Where tonight's images are landing.
Yeah, thank you.
Can you go back to Stellarium for
Yeah,
a second?
not right away. Let me just do one thing. I'm gonna take my gain and I'm gonna knock it up to 350. It's a little higher than we used the other day. Okay. And then we're gonna image this area in just a bit. But first, Stellarium. And back there now, Daryl.
Okay. I thought the seahorse was in Cepheus.
Oh, wait. This is... I'm in LDN 673.
Oh, okay. Izabela says I sound quieter than you.
Well, I don't know why. Let me see if I can do something. I don't know.
Testing, 1, 2, 3, testing.
Oh, you're coming at the same level as me.
Okay, maybe I'm just not talking very loud.
Maybe. Okay. So what was LDN 673 then?
Well, it's another lens dark nebula.
Yeah, it is, but we shot that the other night, and I can't remember.
Yes.
I can't remember if that was fruitful or not.
It's a dark nebula. I thought it looked pretty cool.
All right, we're going to do it then. We're going to go and do, we're going to try 35 seconds. And we're going to do it at 350 gain. That's 100 less than the max. So we're going to get out of here and go into our low light mode.
You just had something bright fly through the lower of the two telescope images.
Yeah, I've got insects out there. Yeah.
Maybe that's what it was.
The temperatures are in the 90s out there. In the in the building right now. And the infrared lights, infrared transmitters on the cameras attract insects that can see them. All right, let's see here. Okay, the first one didn't come in. Let's give us a chance here. Hey, Robert Waters, how you doing? Okay, let's check this one out. Okay, this one came in. Yeah, we got Dark Nebula here.
Yep.
Let's
Kind of
now.
reminds me of Chinese hieroglyphs. I'm looking at an image of it.
Yeah. I'm going to color correct us, and then I'm going to process it a little bit. There we go. Whoa, what was that?
It was me.
That was loud in my ears. Okay. Let's write up our curve. Remember what I talked to you about before? The red, green, and blue curves. The average is this white one. All right. And as we move up that curve, as long as we don't cross the middle peak, we will not start losing data. And we have to color correct, sorry, because we have the moon out, and that's what it's supposed to look like. Moon is going to be setting soon. All right. So this is Lynn's Dark Nebula 673 in the constellation Aquila. And you can see a variety of dark dots in this already.
Looks like Chinese handwriting to me.
Kanji.
Bless you.
Pass through meridian.
All right, the telescope just passed through the meridian. That means that this object is at the best that we're going to catch it. Telescope's pointing almost exactly due south, and right now this object is as high as it's going to get, so this will afford us the best, absolutely best shot of it that we'll get. If you can shoot things when they're right on the meridian, that's the best you'll see them, because they'll be the highest in the sky for you. All right. Let's check here. Okay, no clouds yet. We're good. Okay, there's Lyra. There is Deneb. There's Satyr. Alberio. And that's in Cygnus the Swan. And you can just... Wow. You can kind of see the Filamentary Nebula here. The veil. Interesting. This is moon reflection down here.
Where the telescope is looking right now, those two bright stars, the one bright one and the one to its upper right, over lower right is center. That's Altair
This
in
here.
Aquila. That's the eye of the eagle, yes.
And then this
And
one.
you're just to its right, upper right, I think, for LDN 673.
Yeah, let's go see. There's
Yeah.
Altair and that Asara. So it's here. It is. Here it is. So we're at right about there. That's what we're looking at right now. Okay. We had a thunderstorm out there last night. The AllSky time lapse was just flashes everywhere.
Hmm. We've gotten a couple of storms lately. Interestingly, they were not monsoon rains. They were storms that came out of the northwest.
Hmm.
But the monsoon is still trying to run. It is fading away though.
Yeah. Yeah, we're losing the monsoon out there. Well, we got, like I said, we got clouds all around us. There's clouds southeast toward Tucson, east toward Phoenix, north toward Flagstaff, and west toward California. But they never reach this particular spot. Also clear tonight is Benson, where the other telescope is going. So tonight would have been one of those nights when we'd be running both telescopes at the same time, and we'd be going back and forth between the views of each. So we could go look at the same objects with both telescopes at the same time. One will be at f7 or so, and one will be at f1.8, which is photographically better. Ray is here. Holy cow, Ray Bobel, how you doing, brother? I haven't seen you in a long time. It's so nice to see you, Ray. I've been trying to track you down to see how you're doing. Everything okay? Hello, Gabrielle. Oh, thank you, Gabrielle, for giving us a thumbs up. Really good. Jay Blaine, how's it going, man? As I said, Raymond, very happy you're here. Thank you, brother. You're always good to us, Raymond. And he says, yes, thanks, everything is good. All right, excellent. So here is LDN 673 in Aquila, the eagle. It's a really cool black cloud. Look at this now. This is a very dense area. Could this be gravitationally contracting? Maybe. Maybe. And within here, one or more stars could form if it's got enough hydrogen gas in there. And here's... Go ahead.
The dark cloud just to its lower right appears to have a bright star in the middle of it. That may be a foreground object, though.
This one here?
Yeah.
I'm guessing that's a foreground star, because I'm going to guess that this cloud is probably 5,000 to 7,000 light years away. Maybe more. And that foreground star, if that's what it is, let's go check it and see. Let's get into the middle here. Zoom in. This is the star, right? Or is that the star? Let's go back. Oh, okay. I'm guessing that we might. Okay, so it's the star that's right there. So it's the star just above and to the right. That's this star right here.
Yeah. And you can see that dimmer star straight down below it.
Yeah, it's an A25. How about that? A2. And we have a parallax for it. Distance. Okay. 278 light years. Yeah. So much, much closer than what's behind it. And then this star, a little bit dimmer, is also probably superimposed over the cloud as well. And we can see that too. Because that's this guy right here. And his distance is 731 light years. So look at the difference. Betelgeuse in this view would just blow us out. It'd be just very, very bright. This star is about 20 light years closer than Betelgeuse, approximately, if it's 750. And it's much fainter than Betelgeuse. We're losing a lot of the noise. We got 13 images. We had some failures. We had 4. So that's probably the first one I can understand. So we're getting greens now. So for the most part, we're getting these in here. This is good. Nice. This will make a nice image. So you can start to see some of these separations of the filaments here. The other thing you'll notice is we're now at a sensitivity of 350. That's our gain. And at 350, we get a lot of noise in the image, right? Well, the more stacked we have, the more image sandwich we make, the less that noise will be. So if I can just let this keep stacking up, we'll see less and less of that. A lot going on in here. You can even see now subtle light colors around the edges. See that, Daryl?
Yep. Can you juggle your lines a little bit?
These guys?
Yes.
Yeah. I'm going to try bringing this one in. Pull out a little more detail. Try and color correct again in case we need to. You can clearly see now how brown this looks with illuminated edges. Let's see if we can, if I move it to the right, we might lose that subtle brown because we're going to contrast it out. That's about the best we can do. Can try it just to see what happens if we go right to the very top. Yeah, kind of washes out a little bit. Just to the left. Is that what you meant by juggle my lines?
Yeah.
Yeah. Okay. So there you go. That's looking really pretty. You all know that I love dark nebulae. Dark nebulae are where it's at. That's where life begins. I'm glad you've been watching, Ray. Thank you. Raymond has been a tremendous supporter of SkyTour livestream, and he got some swag from us. Gosh, how long ago was that, Raymond? I'm sure you could tell us. I gave him some crater plates for his support. It was very nice. Okay, we're at 18 images. We had one more failure. Last one was a failure. But that's okay. Good, this one wasn't. Okay. You can see some really nice soft edges starting to come out here.
Yeah.
(2018-ish). Yeah, I think you're right, Raymond.
6 years ago.
Wow. We've been going for a while.
I have a hard time remembering what I had for dinner last night.
Yes, indeed. Raymond says, Mark, I'll need Mo.
Oh, a wise guy.
That's right. A wise guy, eh? No, Mo, no. Come here. Honk. Three Stooges. Yeah, you started in 2014 with Paul and Keith, P&K. You notice they've been kind of silent lately, and that's, I think that's because Keith has become very busy with his work. Okay, let's see here. Okay, that worked too. Good. I'm getting some good images here now. I'll check the AllSky, make sure we don't have to run away. There's some clouds down there, but that's okay. That's the place where we want them to be. Right there, look at that. We have a satellite coming through. Did you see that? It faded actually in this next exposure.
Look, you have some waves of clouds coming up from the
Down here?
south or southwest. Yeah. See several parallel bands of them there.
I do. I'm wondering if those are just reflections from the moon, because the moon is right here. And it's setting. Alright. We'll watch those carefully anyway. Oh, look at that. Go away and come back and it looks better. That's neat. Let's go to the histogram here. Let's try to actually pull out some more detail. Alright. If we come out like this, we're really bright.
Kind of washed out.
Correct. Oh, Raymond, that's pretty cool. Paul and Keith introduced you to what I'm doing. That's excellent. In the beginning, it was just me. Then it was me and Amanda Curran, and then it's me and Daryl and Izabela.
I came around in 2016.
Yeah, that's right. But you weren't like a co-host. You were a co-host. You weren't a co-host until we had this observatory. You weren't a co-host when I was running out front here.
Oh no. I became a co-host in 2017, I believe.
Okay, and that's we might have. I have all the dates actually because I have all the information and the build One of these days I'll do a build video as well of the whole observatory.
No, I was co-hosting when you were running your dome observatory in Connecticut. That's when you and Amanda and I were all on at the same time.
Oh, that's right. That's right. Okay. All right.
I was just making a pest of myself in 2016.
Nonsense.
I was the very first moderator you had, I believe.
See, I trusted you right from the start.
I pointed out to you in comments one night that you appeared to need to be collimating your telescope. And the next time I came by, you'd pinned a mod button on me.
Well, you were offering some excellent advice. It was hard to to collimate it when it's in the middle of the desert, and so you only get out there every so often. And when I went out there to collimate it, I remember going out there early in the morning, like getting there by 9 a.m. and I had to wait until evening to collimate it. So I did a bunch of preparatory work, installed some new software, tested everything, and the building was getting hotter and hotter and hotter as the day went on. I have images of me with a bucket hat on that has the thing that covers the back of your neck, and I'm just like with my head down in the chair. And I think Tara or Marianne took that picture. I'm not sure if I was actually asleep at that point because I was so beat. But it's how we started up.
Actually, when I said you needed to collimate your telescope, it was still the one in Connecticut. It was your first telescope.
That might be when I got the Bob's knobs, which are the little collimator knobs for the people listening to help make the secondary mirror properly aligned with the primary mirror.
Yep. I remember talking about Bob's knobs with you.
Yep. And I got them, and they're actually on the telescope behind me. Yeah. Okay, we're at 29. We'll stop at 30 and move on up the Milky Way. I think we should get a shot of the Pelican and then move up into Cepheus. Okay, 30 saved and save. So if you go here, skytourlive.org, this is our website. It's our portal. There you can donate for what we do. We spend a lot of time, and thank you, Ray.
Thank you, Raymond.
And you could now donate directly on the website if you want, and you can go to this guy up here. This is our Etsy store up there. You see that? And if you want a mouse pad or coasters and anything, glasses, mugs, tumblers, blankets, sneakers, underwear, okay, with our objects on them, you can have them, get them up there. It's pretty cool. Pretty cool.
Does anybody use mouse pads anymore?
Not really. But we make them anyway, just in case. As computers make their way into more advanced configurations, we're going to find that keyboards are going to be non-existent eventually. I think we're just going to plug in, and we'll end up thinking our way, to places we want to go and so forth. Izabela put the link to the Etsy store up there. She also did a fantastic video for our Etsy store, and we're eternally grateful to her for that. She's also the one that built our application, our SkyTour, it's our Stargazer companion, SkyTour Stargazer companion, and it's a beautiful compendium of every single observation. You can search on objects. You can search on almost every single data element that you can imagine. For the last several years of SkyTour observations. So it's really cool. It's a very useful app. You can say, did they ever search for this guy before? Did they ever look for this LDN 673? You look it up, and you'll see if we did, and you'll find out that we did. Okay, and you'll know when we did it, and you can see the picture then, and actually compare it to the picture now and see if something's changed. See, because right now, in this image somewhere, could be an asteroid coming through. Maybe it's that little dot right there, or maybe a little dot up here next to another dot. And in the other image, that asteroid might not be there, or it might be in a different place if it's really distant. So the bottom line is that you can actually make real scientific discoveries with our data. And this application would allow you to do that. Izabela's found asteroids in previous imagery. It's pretty cool.
I see several distinct chains of stars up in the upper left quadrant.
Like right here?
That one. There's a
Right
couple
here?
below it and some above it. And
Here.
the top one, up toward the upper left edge, seems to be a continuation of that dark cloud.
This one right here.
Yeah, it's almost like they're on the same line. The dark cloud to the right then. See all that? Yeah. Are those just happenstance, chance alignments, or are those really there?
Well, I don't know. Now it could be that there's dark dust on either side that's obscuring other stars that might make this look like a more normal quantity of stars for that location. You know what I mean? Who knows?
Well, I often remark on them when I see such. And sometimes the lines of stars do seem to follow dark clouds, and you wonder if they weren't born in those clouds.
Well, we'd have to look at which way those clouds are moving. And if we can get that data, then we would know. And if this cloud, for instance, see these stars, if this cloud was here and it's moving this way, then it's possible that they're leaving a trail of stars behind it. Which is kind of interesting. Okay.
Still looks like Chinese calligraphy to me.
Or Japanese.
Yeah.
Okay. This is it for this guy. I think there's lots of light data we can actually pull out of that. That's neat. Well, this is Lin's Dark Nebula 673, the object in the constellation of Aquila the Eagle. And it's going to be relegated to the night sky for another night. Alright, so let's do this now. Let's bring back our...
Oh, before you take off too much,
Yeah?
you want to check Cor Bor while we still can?
Guess we should. It's going to be pretty low, right?
Yeah. Well, it's east of Arcturus. If you can see Arcturus, you'll be able to see
Well, let's find
Corona
out.
Borealis.
Ooh, that's pretty low. What's its altitude? Oh. You know, I think we can do it. Let's go. We're gonna go all the way to the other side of the sky here, guys. Watch the telescope over my head here. It's going for a little ride. Let's stop right about there. Alright, now, which star is Cor Bor? Well, that's easy to figure out. All we have to do is turn on our annotations and tell it to determine where we are. There it is. So that means that it's down here, just out of sight. Let me move this down. Here it is. So let's bring it up.
Obviously, it still hasn't gone off.
Yeah, we'd be hearing it throughout all the news.
Oh, yeah.
Okay. Alright, so we have this annotation feature that we like to use, and it allows us to identify everything we see in the view. Almost. It doesn't always annotate everything, unfortunately, but that's okay. Okay, well there's Cor Bor. It's known as the Blaze star. And what happens is this is a recurring nova. A nova is an explosion of, or what we call runaway fusion on the surface of a white dwarf star that's orbiting a red giant. And the red giant will bleed hydrogen gas onto the surface of the white dwarf when they're in close proximity. As the red giant grows in size, it grows big enough so that it's large enough so that gas on the outside of the red giant can leak off and go through the common center of rotation between the two stars and end up landing on the surface of the white dwarf. When it does that, that gas on the surface of the white dwarf will just sit there and pile up, getting hotter and hotter and hotter over time. And as that happens, it could reach a point when it reaches a certain temperature, the temperature of fusion on the surface, because white dwarfs are very hot as it is. So if it reaches that temperature, you'll get runaway fusion on the surface of the star. Now, in this particular case, that hydrogen leaking onto the surface is not making the star more massive than 1.44 solar masses. Because if it did, then instead of runaway fusion, we would get a supernova explosion, known as a type 1a. That's Roman numeral 1 with a little a. So type 1a. And those are actually distance candles for us because we know exactly how they occur and we know how bright they are. So if we see one in a galaxy far, far away and we don't know the distance of that galaxy, seeing a supernova, type 1a supernova, will tell us the distance of that galaxy. So it's pretty cool. Now, and how would we know it's a type 1a supernova? By looking at the spectrum. By looking at the spectrum that's coming from the supernova explosion, we can tell what just blew up. And it'll be a white dwarf. Alright, so this is the Blaze star right here. Every 80 years, enough hydrogen builds up on the surface to where it will now have a spontaneous runaway fusion. But the mass that builds up on the surface of the white dwarf is never more than 1.44 solar masses. So after this runaway fusion, the star gets really bright, and then it gets dim again, and it gets back to this brightness. This is prior to the nova. So we have a nova, and we have a supernova. We have a kilonova. We have a hypernova. We have all kinds of different novas. The supernova and the nova are the two most common, with the supernova being the most common.
Can we go to stellarium for a moment?
Sure. We'll back out because I think I know what you want to do here.
Yeah.
Okay, go ahead.
Back out a little farther.
Okay.
You see the crown shape there, folks. Corona Borealis means northern crown. There you go. If you look up in the sky, east of Arcturus, bright star Arcturus, which is getting low in the west now, you can still see Corona Borealis. In fact,
That's Arcturus.
yeah, if you draw a line from Arcturus in the general direction of Vega, if I remember correctly, Corona Borealis is well, it's you'll see it to the east of Arcturus. It's that C shape, crown shape. The bright star in it presently is called Alphecca or Gemma, and when the nova goes off, there will be two bright stars in Corona Borealis. There where the STLS crosshair is where the blaze star is. It's off the second star on the left-hand side of the crown. And for a week or so, you'll see two bright stars in Corona Borealis instead of one.
Yep, and then it'll fade back to that and stay that way for another 80 years.
Borealis means north, Izabela.
Yeah.
Corona means crown. Borealis means north. Aurora Borealis means northern lights.
Aurora Australis is southern lights. Hey there, Kevin O'Neill. He's saying hello to you, Daryl.
Yes, I know. I'm answering him.
Okay. All right. Let's go back here. Let's get rid of our annotations because we know that this is the star. And let's just do a 20-second shot of this. And we'll call it Cor Bor. And there we go. Oh, we're gonna clear that.
Ooh.
I know. Alright, so 20 seconds of Cor Bor. And we're close to where the moon is, so we're gonna get a little bit of a bluish cast.
Yeah. And what we're actually looking at now with Cor Bor there is its other binary star companion. It's a red giant, I believe.
Yes.
And the process that's feeding matter onto Cor Bor is it's drawing matter off the red giant.
Yeah. That's what I was mentioning before with this. I'm gonna take that off so we can see this better. Okay, let's see if we can color correct that. That's better, and then we'll let's annotate that. So there you go. So there's the blaze star under the crosshair. I'll get that a little closer. There we go. So that's a star. And we'll save that image with the annotation so it'll be out there for you. Okay, it's out there. And don't worry, we won't lose it. It's right there.
Izabela asked, are we going to look at the seahorse again? I know you mentioned it earlier, though. You may have been thinking of LDN 673.
No, I was thinking that, I was thinking Aquila, but I had the name wrong. It was 673, not the seahorse.
Okay.
Maybe we'll do it, yeah.
Izabela says, Mark, would you mind taking an astrometric image, please?
I just did.
Okay.
and she wanted me to do the annotation.
Yeah.
Is that what you're talking about, Izabela? Because I just brought this up, and I hit save. Okay. Yeah. That's always helpful. Okay. Just save that and save it exactly as seen. That's enough for this guy because we know it hasn't gone off yet. And boy, yes, it would be great to see it go off while we're watching it. We'd go down in history. Okay, let's zoom in now. Alright, so I'm going to say while we're here, might as well head up a little bit and see the Measure 13.
Cool.
Oh. We're going to go a little bit. There it is. Yeah, that's a beauty. As you said the other night, Daryl, every globular cluster has its own unique look.
Yeah. This is Messier 13.
Yeah.
This is the finest globular you'll see in the northern sky.
Measure 22, southern sky technically, but it's pretty.
Yeah.
I put GC because it's a globular cluster. Alright. Right now we're going to be searching for a guide star here in just a moment. It takes about 14 seconds to get the guide star. Meanwhile, I'm going to set up the exposure of 20 seconds. I do not know anyone doing studies of the straight lines of stars, Ray. With all the stars out there, it's possible we're looking at just chance alignments, you know. But I'm sure there are some that are the result of processes out there.
Deep sky clock event closing.
Okay, let's clear this. So we see our Measure 13. This will be pretty. Watch this. Boom. Look at that. Oh. How pretty is that? I'll pull this off our slope here. Lift it a little bit to the left. And now I mentioned before, globular clusters are halo objects. They orbit the whole galaxy. They plunge through the disk. They come up through the disk again in some cases. And during that process they could acquire more stars or shed stars. That's not how they formed. It looks like there may be black holes in the middle of globular clusters, at least some of them, and I think that would be responsible for the cohesiveness of these clusters. And they're not if there's black holes in there, they're primordial black holes. They're black holes that were formed when the universe was formed, and that would go into making some of the missing mass that we know we have. So this I'm gonna move down, and I'm gonna take our mid-level down just some more to resolve those central stars. Let's see how that looks.
And I can see the propeller already.
Yeah. Let me see if I can make that more obvious. Well, that makes it more obvious, but it kind of ruins the view. The stars that make up globular clusters, when we look at their spectrum, we find that they basically have hydrogen and helium and not much else. Now, that means that they were made at a time when there was only hydrogen and helium in the universe. And that is a long, long time ago. In fact, these are among the oldest objects in the universe, globular clusters. We're looking at the ancient universe when we look at these. And they're called population 2 stars, which you would think that they'd be population 1, meaning earlier. But no, population 2. We astronomers love to confuse you. But the particular chemical makeup of these shows us that these have been around since the very beginning of the universe almost. And that means that, it means that they don't have a whole lot going on. That also means, by the way, that these particular clusters probably don't have any planets in them unless they picked them up as they went through the disk of the galaxy. Because planets need a variety of materials to form. Magnesium, calcium, right? Tungsten, and all the other chemicals in there, carbon. And unfortunately, in this particular case, this is actually kind of like a cluster of stars that were made before any of those other elements were made in other stars. Remember, all the dark dust we see comes from many supernovae that blast this material out to the universe. Pretty cool. Michael Hedrick, hi there. Fantasy, hello. Nice to see you too. This is Measure 13. A beautiful cluster. Let's color correct it a little bit. Okay.
We've doubtless talked about this before, but folks, if you look from the center of the cluster, look just to the lower left at about 8 o'clock, and you can see a 3-lobed propeller shape. And that's what that's called, is the propeller. Just what is the propeller? I mean, I don't think it's a dark cloud. Is it just a contrast effect? Less stars along that line of sight? Is it something real?
Yeah, because globular clusters don't have a lot of dust in them.
All right.
So I would guess that it's probably just this particular case, a chance alignment of the stars. So you've got one lobe of the propeller here. You got one lobe of the propeller here. And you got one lobe right here. So you got a 3-lobe propeller. Now, no, it doesn't mean you got a cluster going through the universe, okay, with a propeller.
Well, yeah. I mean, it's just one of those things that's,
Yeah.
as Marc mentioned, globular clusters all look kind of different in detail. They have certain features to them that make them unique. M4 in Scorpius has a bright line of stars right down the middle. M22 looks like its own cluster, and lots of them do.
Oh, this is an exploding snowball of stars.
Exploding?
An exploding snowball of stars. That's what I have always thought of globular clusters as. They look like an exploding snowball of stars.
Looks like. I mean, it's not really exploding.
Well, of course not. It's a term. It looks like it's like just blasting outward. It's an exploding snowball of stars. They're beautiful. And they're all different. And they're at many different distances too. This one is closer to us than the next one that's near it, Measure 52, I believe. So this one, if we look at this guy, its distance to us, from us, is 25,000 light years. And
when we look at Messier 4 in Scorpius,
yeah,
which is gone for the season, I think.
almost.
It's the closest globular to Earth. I want to say 4,000 light years. And it's actually inside the Milky Way.
Yeah. And your eyes aren't playing tricks. There is a galaxy right here that you see. And let's do an annotation and see if our annotator will recognize that galaxy. And sure enough, it does. And that's not all. It recognizes IC 4617, another galaxy right here. NGC 6207 is this galaxy up here in the upper left. And of course, Measure 13 is the Hercules Globular Cluster. And this star is Hipparchus 81848. And we'll save that annotation. There we go. So you'll have this to look at too if you want to see what things are what in these images. And we have another. I just yawned. We have one here, NGC 6196. Okay. That's another galaxy. NGC 6199. That's a star though, so I don't know why they call it NGC 6199. Maybe it's a star with something associated with it. Alright, so we save that. And we come back to our exposure. Well, you can curse the Starlinks all you want, but you know what? Starlink brings you SkyTour. So there. I guess we gotta live with it. Really pretty.
Mark, it's time for my 10:30. Excuse me. I'll be right back, please.
Okay, I'll be right here.
Right back.
Okay. Yeah, Michael, I like the annotation in real time. It's really cool. Hey, Red Angel, how you doing? Okay, let's save this right now. We have that. Save exactly as seen. Now we'll get out of that and go back into our low light mode. Okay, there we go. Let's find out what our sky looks like right now. Okay, because we're over here. If we look at our constellations, there's Arcturus, Corona Borealis, and Hercules right here. All right, and this is Hercules right here, and Messier 13 is right about there. So it's kind of low for us, but there's our Milky Way, and you can see these beautiful tendrils of dark in there. Gosh, that's gorgeous. All right, I'm gonna have a camera like this at the Benson Observatory as well, because why not? All right, so let's come out of here. And we're going to come back toward this. All right. I just want to check this out. It's pretty. I'm running over to the Trifid Nebula right now. I think it's just below here. Oh, yes, it is. There we go. There we go. Sorry about that. I had a, I was only going at 167 milliseconds and not 1 second. So it's like a tenth of a second. So we weren't seeing too much. All right. Now I'm also noticing that by moving the telescope around, we may have lost our critical focus because we have the mirror flop condition that occurs. So I will focus. Welcome back, Daryl.
Thank you.
Okay.
Looks like the Truffle Nebula.
That's right, it's the truffle. Truffles have tridges. Alright, so now let's go here. We'll identify a number of stars. We have 11 that it can identify right now. It samples each star and it's going to go through a focusing run, and it's going to get the stars down to a minimum size. That minimum size is the bottom of a curve that it's generating. And you'll see that curve being built as it moves. Then we will lock it on that lowest value that we get, and then we will tell it to save that as the best focus position. If I leave it alone, it'll just automatically go to it. Look, we're up to 146 stars, 150 stars from 11 stars. Now it's going back 148. So we found the deepest part of that curve, and now we're going back up the other side where it's getting out of focus again. So you can see that a curve is probably the line's going to appear right about here in just a couple seconds. You'll see a line right there. That's my guess, right here. There it is. There's our parabola. That's our curve. The lowest point in this curve is the best focused position. So we can just say go to best focus. Now the telescope will automatically go to best focus. And you'll watch the stars become tiny little pinpoints. Okay. And now we're good. So if we get rid of this, you'll see how pretty it looks. You'll see how the stars are all little perfect pinpoints. Alright, the Trifid Nebula is a beautiful combination emission nebula and reflection nebula. The red is hydrogen emission, and the blue is basically reflected light off of dust from the star. It's scattered light, like the blue sky. Scattered light molecules take in blue light and shoot it back out in all directions, and that makes a scattering nebula basically, and that's what we see. It's going to be around the whole thing, but the red is right here focused. Okay, so we're going to do a 25-second shot here, and off and running. Now we're going to go into low light mode and let that 25-second shot. Remember, we're at 350 gain right now. So we should expect to see a little bit more of that nebula around the Trifid Nebula. Let's see what we get for our first image. Our first image looks like it was... Okay, must be wind picking up out there because it's above the threshold. That's all right. It's just windy. Benjamin, how are you, Benjamin Izabela? Nice to see you. Oh yeah, look at that. Yeah, we're getting wind out there. Look, the whole sky moved. No, that's pretty. Nothing compares to standing under that though and looking up. When you're in the building looking up, it's like, wow. If this third one does that, I'm going to... Okay, we're getting close, so I'm going to move my threshold up to 8.84. Anything above that, it'll reject. Anything below that, it will accept. Oh, 9.04. Okay, if I get one more, we'll abandon this object for tonight. Try something else. We're just getting so close. Alright, I went 9.08, which is what this one was. If it's less, we should get at least one. Hey, look it, we got one. All right.
Ta-da.
Ta-da-da-da-da. Color correction. Color correction is not quite color corrected. All right, let's pull this in.
What's the yellow message across the top mean?
I wasn't sure about that. I was trying to do a color correction and I got an error of some kind. But okay, there we go. So this is the field over here. This is in Sagittarius. You can see lots of stars, lots of red nebula. That's actually there. Then you got this emission nebula, and the stars in the middle are ionizing the hydrogen gas in all directions. And it's interesting how it tapers off after a certain amount of number of light years out of the middle. Okay. So then, but up here, this blue extends all the way around. So there might be blue reflection nebula behind this. So we have the Trifid here, and then the blue might be here, and it peeks out over the top here, and is down below as well. And then there's dark nebula in here that you can see. Let's bring our mid-range down. There we go. Now you can see that more clearly. That's really pretty.
It is.
Cindy, how are you? Cindy Murphy, Daisy and Zoe, hi guys.
Star cluster to the upper left near the top.
Yeah?
That's Messier 21, is it not?
I believe it is. We looked at it last time. We can annotate it and confirm that, because I think it is. Yeah, Messier 21 open cluster.
Okay. And surprisingly, not far from Messier 20.
That's right. Okay. I'm going to pull us down into the weeds here just to get a better look at this. That's a beautiful nebula. Isn't this amazing, guys? You're seeing something live in the universe right now. And this is live. I like to think about it as, this is thousands of light years away. The light left it thousands of years ago. Okay? And the light that just reached our camera finally reached the destination, and somebody actually saw it. You did. We did. When we go off this object, the light will keep coming to the Earth, and it'll all get missed. Unless someone else around the world is watching it. And undoubtedly that's true.
Can you zoom in on the lower part of the red?
Yeah.
You have a little kind of a loop of nebulosity there.
This here?
Yeah.
Yeah, that's one of the hot spots. It could be the beginning of a pillar. Material being driven away, a little denser at the top here. And the star's energy could be driving that stuff away around it. No coincidence, I don't think, that it's pointing right at the central star there.
Yeah.
Yeah.
The left side of it pretty much makes a straight line pointing right at the bright star.
Yeah. There's actually 2 stars here. It's not an oval. It's 2 stars. It's 1, 2. But for us to show the nebula, we have to overexpose those stars, and they're so close to each other that you don't see them as separate, unfortunately, unless you do a very low exposure. Well, okay, this image is rejecting more than it's taking, so we won't keep it. We'll come back to it at some other point. It's not working out, so we're gonna get rid of it, and let's come out. And now we'll actually show you those stars now. One second of this. Now you can see that second star.
Yeah.
In fact, let me do this and zoom in, show you the second star directly. There you go. Parent and little tater tot.
I thought for a moment there it looked like it was like a little ear. I still see it. The brighter star above, I was seeing like a little ear sticking up at about 11 o'clock.
Yeah. Some
Maybe
of
that's
that.
just twinkle distortion or something.
It's probably what it is, because remember, we got wind out there right now. Yeah. Yeah, wind is a nemesis at times. Yeah. And we're pretty low right now, so the fact that we're getting this wind means I'm not going to take us to higher elevations tonight. I do not wish to do that. Alright, let's see though.
Oh, you could try.
Yeah. Yeah, I won't be doing the seahorse tonight.
Okay.
Yeah.
I know that image I shared a couple of nights ago,
Yeah.
seeing what was just out of frame to the left of the seahorse, what they call it, the Flying Bat Nebula.
Oh yeah.
And the Squid Nebula.
Yep.
And one other object, I believe. Could probably make a nice 2 or 3 frame mosaic sometime.
Absolutely. Let's try. Yeah, measure 31 is just rising up. It'll be a little bit below our pole altitude, so we won't be able to get to it right away. That's not going to be easy. But let's see. Cassiopeia. Okay, and then we have
There's the Cocoon.
yeah. We haven't tried the Cocoon with this camera yet. We could try it.
If you like. Elephant's trunk, getting into that part of the sky.
Yeah. Let's try the Cocoon. Let's go there and see if we can grab this. It's gonna go way up and out the back. This looks like part of it. I'm gonna drop us down to 300. Okay. And let's do an annotation here. Figure out exactly what we're looking at. Okay, so the Cocoon is not in this view. There it is. This is a... Is this Caldwell 19? Is that what that is? I guess that's Caldwell 19. Caldwell is another catalog, guys, and so yeah. All right. No. All right. So let's get out of this for a minute. The Cocoon has a trail of dark nebula off to the side. You can see the Cocoon's shape here. You can see the colors of the hydrogen. And as we move over a little bit more, you'll be able to see that there is a line of dark dust that goes up here. So we'll see what we can do. Let's see if we can grab it. And it's a pretty nebula. First things first, let me zoom in because I've got the telescope way back now. And I want to make sure that our focus is good. Okay. I have a question of the night. Are there worlds out there where an unbalanced orbit or double orbiting exoplanets would cause the extraterrestrial inhabitants to feel more gravity at one time? Interesting question, Michael. I have an opinion, yes, I'm about to tell you. Any orbit like that of a planet might tend to be extremely difficult because life requires some form of constant conditions, and without those constant conditions you might not find that life could evolve at all. I mean, give you an example how sensitive things are. We have an asteroid belt in our solar system, of course, and in the asteroid belt people say, well, how come it didn't form a small moon or a small planet? And the reason is because of the planet Jupiter. Jupiter just tugs on them just enough as they go around in their orbit so that they're moved a little bit. And that tiny bit of movement that happens only near Jupiter in the entire vast orbit was enough to prevent them from forming any type of a large object of any kind. So regarding double orbits, those would tend to be extremely tricky to pull off. So I don't think that that would actually foster life. I think that might actually injure the chances of life. Let's see if this one will come in. Okay, that one came in. All right, let's see what we got for our full width. 7.29. I'll drop us down now. Keep us in that range. All right, let's go back to the histogram. Let's do a color correction. And then this. Boom.
Whoa.
Yeah. As you can see, guys, there's that trail of dust. And that's really pretty. This is the first time we've ever photographed the cocoon with this camera. Look at that. Wow. Nice. Michael, you're funny. I'm glad I could answer the question, Michael. Yeah, this is Benjamin Izabela says, beautiful red haze. This is the emission nebula surrounding the star inside that is causing this. And how this tail of dark nebula formed is something of a mystery. However, I'll say this. This tail was here before this. This thing is what happens when you have the formation of a hot star that happens inside of a dark nebula. And we've talked about this. The star will wink on and boom, it'll ionize the hydrogen gas around it and make this red glow that we see. It'll also make a blue glow. You can't see it yet, but there's a blue glow mixed into this. That's just the scattering by the dust of the star's blue light. So it's really cool.
What we talked about earlier tonight, stars appearing to be in a cloud. This one really is in the cloud.
Yeah. It absolutely is. And you can see now, you can see how there seems to be like a haze around these stars. That's because of the fact that we're seeing blue scattering being done in here. That's really pretty. This is the first time we've seen it with this camera.
Mm-hmm.
Very nice. And this is at 300 gain. Wow. And this will be our last object for tonight, guys. I have to get up earlier.
Interesting details coming out in the cloud there. Darker areas
Yeah.
and lighter.
Yep.
Actually, quite a bit of gradation to the red.
Yeah. Let's back out a little bit. Go to full size here for this. And let's use this histogram to bring out all the stuff that's in here. Yeah, look at that. There's a lot of blue in here. And this is a massive dust cloud within which the star formed. And it kind of makes it look like it's leading to charge with all this stuff behind it, but it's not. This cloud was here first, and this formed in it to make this. Oh, that's pretty. I want to do that. Wow. Alright, we're going to go to 15 here, which is the next exposure. So thank you guys for coming out tonight. This is a lot of fun having you with us tonight. I have to... there's a couple reasons why I got to close early. One of the reasons is that I have to be up a little earlier tomorrow, but that's not really the reason, because I always push through and get tired anyway. The other reason is that we do have these clouds out there, and I can't predict when they may or may not even turn and come toward us. But let's go check out our AllSky, see if they're here. Not yet. Okay, it looks nice and clear, but boy oh boy, I've watched it change within 15 minutes. Good night, Izabela.
Good night and good morning, Izabela.
Cosmic Ray asked, how do you know the dark nebula was there before the bright nebula? Because, Ray, these dark nebulae, being the result of supernovae, were strewn throughout the galaxy. And then these nebulae that we see here, they're pop-up nebulae. They form in the molecular clouds that are out there. And they're full of hydrogen. There's hydrogen all throughout here, hydrogen gas. Hydrogen is the most abundant element in the universe, as I mentioned. These things here, these clouds are made of carbon and silicon. Carbon's the fourth most abundant element in the universe. Right? So what will happen is, in these clouds, you'll get an area of local density, and they'll start to collapse. We see this in a lot of places. We see globules. Bach globules that are forming into star systems and planetary systems, and they could end up doing exactly what we see here. So this right here was within the dust. You can see, if we zoom in, you can actually see the dust all throughout this area, all throughout this area. So you have hydrogen in here, and you have all this dust. So whatever star is causing this to be illuminated, it probably formed in here, and it's roughly spherical because that's the ionization radius for that particular star.
You can see a couple of quite dark clouds at
Right here.
at 1 o'clock there. Yeah.
Yeah. Yeah, there's one here. One there. This is more detail than we are ever seen in the Cocoon. This camera is really showing it out well. Oh yes, I took an image of the moon earlier, Izabela. She's right. Okay. Look at that. That's pretty. Oh my, sorry. Okay. Interesting now, this dust trail has a distinctly brown look to it. When we've imaged this in the past, it's always looked kind of black. So now we're actually seeing a little better tonality on it, which is kind of interesting. And that, of course, we'll try to draw out when we process. That's really nice. Beautiful. We're going to 25. And we're at 300 gains, so we should see some pretty good details in that cloud upon processing. There we are. Save, and save exactly as seen. Alright. Well, these images will be up on skytourlive.org in just a few seconds, actually. Less than 30 seconds. So I want to thank you guys for coming out and joining with us tonight on the SkyTour live stream with myself and Daryl. Once again, I'm Marc D'Antonio, and that's Daryl Mason in the vaporware out there that you hear time and again. And so we hope to see you again. And my schedule, by the way, is such that I will be going out to Arizona to work on the Benson telescope end of October into November. And we have some other surprises in store as well. So that should be good. So thank you guys for coming out, and I'm sure we will see you next time around. So I hope you had a good time tonight. Please leave questions or comments in the chat, or not chat, but the on the video, and I will answer questions that come in. All right. So have a good night, guys, and we will talk to you soon. Good night.
Good night, everybody.
Good night, everybody.